Welcome to the ChemDoctor, and the purpose of this video is to determine the pH of a 5 molar phosphoric acid solution. This is an important kind of problem to know how to solve if you're a student in general chemistry, for example, at the university level, advanced placement at the high school level, or even a high school level chemistry class will have these kinds of problems. Now, the issue is that we're dealing with a polyprotic acid. What that means is that this particular acid has more than one proton that can be donated to solution. And we see that for a polyprotic acid that we can break the ionizations into separate equilibrium steps where the actual equilibrium constant can be calculated. And we see for phosphoric acid, since there are 3 protons, that we can break the ionization of phosphoric down into 3 steps, each with its own unique equilibrium constant. Now, the key to being able to calculate the pH of a polyprotic acid in general is to realize that the first thing that you've got to do is evaluate the equilibrium constants. And we see that for this particular polyprotic acid that the equilibrium constant for the first step is very large compared to the subsequent steps. And what I'm going to do is go ahead and insert the ratio between these numbers. So in other words, if I took 7.5 times 10 to the minus 3 and I divide it by 6.2 times 10 to the minus 8th, and the reason that I would do that is to point out to the viewer how many times more powerful the first equilibrium is by contrast to the second. And what you get when you take that ratio is 121,000 to 1. All right, so the first step of this reaction, the first step in the ionization of phosphoric acid, basically is the dominating equilibrium and is going to be the major force in providing a hydronium ion in the solution, and therefore is the equation that's going to control the pH. So to find the pH of this solution, what we're going to do first is go ahead and calculate the H3O plus based on the first step of the reaction. So I'm going to rewrite my ionization equation over here. So we have the phosphoric acid in equilibrium with the hydronium, H3O plus, plus dihydrogen phosphate. And the Ka for this value, or for this equation, excuse me, is going to be equal to 7.5 times 10 to the minus 3. Now, there's a couple things you need to remember about this. Oh, okay, and we have a 5 molar solution of it initially. Okay, there's 2 ways you can get into trouble in a problem like this. The first is that we needed to ascertain whether or not the equilibrium constant for the first reaction relative to the second is suitably large enough that we can ignore the hydronium being produced by the subsequent reactions. In this case, we don't have a problem with that. The second thing is, now in terms of our calculations, is whether or not we're going to be able to neglect X. And there are 2 factors that come into that. The first is the size of the equilibrium constant, which we see in this case is in terms of magnitude is around 10 to the minus 3. So actually we're in a place right here that we need to be careful, because generally speaking, when we get down around 10 to the minus 3, or when we get up around 10 to the minus 3, we're in a situation where the percent ionization may surpass 5%. The other thing is the concentration of the initial acid. We see in this case is a fairly high molarity. If this was a low molarity, it's almost certain with that issue in combination with the larger equilibrium constant that we might have to use the quadratic equation to find the hydronium concentration here. In this case, we should be okay because we're dealing with a relatively high concentration of phosphoric acid. Let's go ahead and see though. So you want to set up your ICE table. In my class, I call it a before and after. So initially there's going to be 0 of the H3O plus and 0 of the dihydrogen phosphate. At equilibrium, we're going to have 5 molar minus X, and then we'll have X of the H3O plus and X of the dihydrogen phosphate. When we set up our expression, we're going to have X squared over 5 molar minus x, and the whole thing is going to be equal to 7.5 times 10 to the minus third. So what we're going to do is assume that we can go ahead and neglect the x. So I'm going to go ahead and cross it out here just to be black and white about it with the viewer. And then we need to go ahead and do the algebra. So we're going to have x squared is going to be equal to 5 times 7.5 times 10 to the minus 3. So my x is going to be the square root of this value. So it'll be 5 times 7.5 times 10 to the minus 3. So my x, which is going to be equal to the H3O plus, which is also equal to the dihydrogen phosphate, is going to be equal to 0.1936 molar. Now, I want to very quickly, I'm going to just do it over here in this little spot, find my percent dissociation, because that's the same calculation as the 5% rule. So it's going to be 0.1936 divided by 5 times 100. And what I get for my percent is about 3.8. All right, which puts us well within the 5% rule, which makes it okay to have neglected my x. So this is in fact my concentration of H3O plus and the dihydrogen phosphate. If I want the pH of this thing now, then I'm going to take minus the log of that value. Minus the log of 0.1936. And so the pH of the solution is going to be 0.71. All right, now, almost always in these problems, they're going to ask you for the ultimate anion down here. And since we're dealing with a polyprotic acid that has 3 protons in it, then we're going to have to work our way down. So the next ionization in question here is going to be H2PO4 minus. All right, in equilibrium with hydronium and hydrogen phosphate, which is HPO4 minus 2. The Ka for this value is 6.2 times 10 to the minus 8th. All right, now we have a common ion basically issue here, and what I mean by that is that we have known concentrations of 2 of the components. All right, so we have 0. Let me clean that up a little bit. All right, so we have 0.1936 molar of the H2PO4 minus. We have 0.1936 molar of the H3O plus, and we have 0 of the HPO4 minus 2, and this is my before, all right, in your ICE table, the initial concentrations. When this comes to equilibrium, the shift will be 0.1936 minus x for this. It'll be 0.1936 plus x for the H3O plus, and it will be x for the HPO4 minus 2. Now, note we have a special situation here. We are going to neglect the x because our equilibrium constant is suitably small. The special case I'm talking about is the fact that when we do neglect the x, so let's look at our expression here. We're going to have x, and if we're neglecting the x out of both of these sums, we're going to have 0.1936 in the numerator, and we're going to have 0.1936 in the denominator, and the whole thing is going to be equal to 6.2 times 10 to the minus 8th. So you can see that in this case, these two values cancel out. So my x value, which is equal to the concentration of the anion for this step, so concentration of HPO4 minus 2, is simply equal to the equilibrium constant. So 6.2 times 10 to the minus 8th. All right? You're going to see that this special case happens with all polyprotic acids in in the second step of the reaction. When we move to the third step here, that's not going to be the case, because you see we're going to have different concentrations of common ions. So ultimately, this is the last thing that we need to find. So let's go ahead and do that now. So we're going to have, oh, and by the way, I'm going to leave it for the viewer to go ahead and calculate your 5% rule here. So you're going to use this here as your x value, and you'll divide by 0.1936 times 100, and you'll see that it was appropriate, in fact, for us to drop the x. All right, now let's go ahead and move on to the last part of this. So we need our last equilibrium, so we're going to have HPO4 minus 2. All right, and it's going to be in equilibrium again with hydronium. And then the ultimate anion, which almost always is asked for in these kinds of problems. That's why the viewer really needs to spend some time with this. All right, in terms of our before, for the HPO4 minus 2 now, this is going to be 6.2 times 10 to the minus 8 molar. The H3O plus, though, on the other hand, is 0.1936. So these two values are not the same now. And then we're going to have 0. Now at equilibrium, we're going to have 6.2, times 10 to the minus 8th molar minus x. The H3O plus will be 0.1936 plus x, and then our phosphate's going to be x. So setting up my expression, we're going to have x, and now I'm going to go ahead and neglect. So I'm going to drop the x out of the sums. So I'm going to have x times 0.1936 molar divided by 6.2 times 10 to the minus 8th. And the whole thing is equal to the equilibrium constant, which is 4.8 times 10 to the minus 13th. So my x value is going to equal 1.54 times 10 to the minus 19th. And this is the phosphate. All right, and with that, I'd like to go ahead and close the video. You can find more videos that ChemDoctor has produced at www.chemdoctor.org. Thanks again for visiting and taking the time to watch the presentation, and please come back. All right, have a good day, and we'll catch you on the flip-flop.